Good afternoon, everyone, and welcome to today's CANSSI Ontario Statistics Seminar Series event. My name is Hussein Warzar, and I'm a PhD student at the University of Windsor. It's my pleasure to serve as the moderator for today's seminar. Today's talk was originally planned as a hybrid seminar here at the University of Windsor. Unfortunately, due to travel delays, Dr. Melody Ghahramani was unable to arrive in Windsor as scheduled. We are very grateful that she's still able to join us remotely and deliver her presentation online. It is now my pleasure to introduce Dr. Melody Ghahramani, full professor in Department of Mathematics and Statistics at the University of Winnipeg. Dr. Ghahramani completed her BSc in Mathematics and Statistics at the University of Manitoba, her master's in statistics at Simon Fraser University, and her PhD in statistics at the University of Manitoba. She has also made many important professional contributions through her service to statistical community, including roles with the Statistical Society of Canada and CANSSI Prayers. Today she will present her talk titled On Time Series Regression Models for Zero-Inflated Proportions. We are delighted to have her with us today. Dr. Ghahramani, thank you very much for being here. I'm happy now to turn the floor over to you. But before that, I'm asking audience, please, if you have any questions, share them in the chat section, and she will answer to your question by the end of this seminar. Thank you.
Thank you, Hussein. I'm going to share. Thank you very much, everyone, for joining me on this presentation. My talk, I've changed the title just a little bit, a couple of words, still on zero-inflated proportions for time series models, but I changed the word semi-parametric to distribution-free. You're going to see why towards the end. This talk is joint work with Antonio Axalan, who was an undergraduate when we worked together on this problem in the Math and Stats program, as well as Dean Slonowsky, who is a faculty member in the Department of Mathematics at Vancouver Island University. So thank you. Thank you for the invitation, CANSSI Ontario, in particular the SPARK program, through which Hussein and I have been chatting a lot, CANSSI Ontario staff, for all the legwork that you did to make this happen. Sorry I couldn't make it in person. I'm looking forward to giving my talk here today. Also, members of the Department of Mathematics and Statistics for the legwork that they've done. And I'd like to acknowledge my colleague, Nora Casson, in the Geography Department at the University of Winnipeg, whose research program motivated the talk that I'm going to be giving to you today. Okay, so the outline of my talk's as follows. I'll give the motivation, and that will lead me into the class of zero-inflated beta time series regression models, where we estimate them through a framework known as partial likelihood. I'll discuss a couple of simulation studies, followed by a real data example, and summarize what I call part one. Then I'll give a small taste of extensions to this work through a class I'm calling distribution-free regression models, and these results are very preliminary, and I'd appreciate any feedback from the audience as to how to proceed. I have some questions of my own, actually. Okay, so what was the motivation? Well, so Nora and I were speaking, and one of the aspects of her research program had to do with evaluating trends in winter climate variables. So for example, in this paper in ecological applications that came out in 2019, Nora and her colleagues assessed trends in a set of winter climate variables pertaining to northeastern North American forests. And so based on some non-parametric tests, they came up with the analysis that, in fact, there have been trends, changes in the trends of these climate variables. Here is the geographic region where they were studying. You'll see 37 monitoring stations on daily temperatures, daily minimum, daily maximum, some other temperature values. This data is available freely from Environment Canada, and you'll see some delineation. It was because in their analysis they had broken down the region into west, central, and eastern. So they looked at 100 winter years of daily temperatures. And so what is a winter year? A winter year is defined to be, it starts at November 1st and then ends on May 31st of the subsequent calendar year. So once again, they looked at some winter climate variable indicators. What are they? Well, it was, I think, I believe a list of 11. I'll just give you a few that we could look at. For example, based on the minimum daily temperature, we have an index, and also based on the daily maximum, as well as some other variables such as snow depth. And these variables, they're important for human beings in terms of that could be important for human health, social reasons, economic reasons. And in red, you'll see I've marked down extreme cold day, which also is called in pine beetle kill day. It's defined to be the day on which the daily minimum temperature is less than minus 18 degrees Celsius. So why is that a concern if there's a trend in this variable, such as it's starting later in the winter year and ending sooner, for example? Well, there is a concern about the northward migration of the southern pine beetle. And you can read their paper for the definitions of the other winter climate variables. But this is with Antonio and I, when we looked at some exploratory data analysis, this variable has motivated our study of today's talk. So, for example, you might see a plot like this, a time series plot, where we have the proportion of sites on each day that experienced an extreme cold day. And the pattern is, well, we're not seeing usually any winter extreme cold day in the beginning of the winter year. At the end of the year, winter year, we're seeing it in the middle. But we might see something like where at the last winter year, there could possibly be a change, such as a change in the level of the series, a change in the variability. Not too clear about whether there's been a change in the zeros um, uh, in that winter year or not, but we looked at this and thought we'd like to test for this in a regression framework, because at the time when we did this investigation, we hadn't seen that where we had models for zero-inflated proportions, at least not where there was potential serial dependence, because the data being measured on a daily scale, we thought there's likely serial dependence, and we would like to adjust for that. Furthermore, what are the non-zero proportions like? They're typically skewed to the right, and once again, we're showing a preponderance of zeros in such data. So we wanted to model these features in a regression framework. Setting up some notation, let YT be our observed response series of proportions that may on occasion take the value 0. Standard time series notation, the script ft-1 is the sigma algebra generated by the response series, lagged response series, and any covariates. Now, the thing that I want to emphasize is that here are covariates. We're going to say they could be stochastic or deterministic. And that's why you will see in the next slide, I'm motivated to develop this framework. We're motivated to develop this framework in the partial likelihood framework. And finally, conditional on past information. We assume that our response series YTs are independent observations. Now, before I go on, we've used the word zero-inflated. I personally don't really like that terminology. There's no inflation. If the proportions are in the open interval 0, 1, then I should call them this data zero altered, for example. But that's a word that you do see in the literature. But because our investigation is an extension of a model that was termed zero-inflated beta regression for cross-sectional data, I thought that in keeping with that, I convinced my colleagues that we should um, label our model zero-inflated. Okay, so what is the model? We're going to say that conditional past information, the density is a mixture of a beta distribution, a density, and a degenerate distribution with point mass at 0. Okay, so this I is the indicator for a 0. And this beta distribution, you may or may not have worked in this with this model before. This is a beta regression model here where it was the beta distribution reparametrized to allow for the inclusion of covariates. And it first appeared on the literature in 2004, and it's by Ferrari and Cribari-Neto in the Journal of Applied Statistics. So we can, going back here, the beta distribution, once again, it's characterized by a mean and a so-called dispersion parameter, and they may be influenced by covariates, and our zero inflation parameter, alpha t, may also be influenced by covariates. And the approach is very flexible in that we don't have to have the same set of covariates influencing these parts. And so here, the rho, the beta, and the gamma are the parameters which we wish to estimate, and the x, the z, the w are covariates. And I have some very generic notation here for covariates that you'll see in time series literature that I can point to. But just keep in mind that once again, we could have lagged responses in each of these covariate vectors. We could have deterministic or stochastic lagged components and functions of them. And this process, the conditional mean depends on the mean of the beta distribution and the zero inflation, and we have an expression for the conditional variance. And so if you set your so-called zero inflation parameter alpha t to 0, you get back the conditional mean and conditional variance of a beta ARMA model. So that Cribari-Neto then has collaborated with this is Rocha's probably his student, to develop a model for beta data that it has a sort of an ARMA structure to it. I will reference these moments later, much later at the end of my presentation for the extension work. Okay, so I mentioned that we wanted to develop estimation within partial likelihood framework. What is that? Well, as students, we first, at least maybe this was the case for me, I first came upon partial likelihood in a survival analysis course. I'm not sure if partial likelihood is mentioned in a time series course, a graduate course. So I thought I'd very briefly review what I mean by that. And to keep things simple, we're going to assume that we have a response series yt and a single time-dependent covariate xt. So you observe x1, then you observe y1. You observe x2, then you observe y2, and so on, xn, then yn. Well, what would the full likelihood look like? I've written it down. We'll take the marginal uh, density at x1 plus this term in the middle, which is a product of conditional densities of xt given past information, and then we have a product of conditional densities of yt given some past information. And you know, David Cox said, well, under certain conditions, we may be able to we can do valid inference about theta just based on this latter term. And this latter term is called a um, partial likelihood. And so it's a way of getting away from, uh, having to specify the conditional distribution of the covariates given the past. Okay. And so, if you want to know more about partial likelihood in time series literature, this is a very nicely written book. The first several chapters discuss partial likelihood in general, and there's partial likelihood for time series following generalized linear models, and another chapter on categorical time series regression. And you'll see um, how it's developed for each of those types of models. So, taking our inspiration from the literature by Kademan, Phokianos, and the various co-authors, what is partial likelihood in this setup? We're going to take the product of the conditional densities of yt given the past. Again, keep in mind this past information may include stochastic covariates. If you don't have stochastic covariates, well then you're back to conditional maximum likelihood estimation that we're familiar with from our time series training. And the goal is to estimate the zero inflation, the mean parameter, and the dispersion vector parameter in this problem. And so, we'll have an expression for the log of the partial likelihood written down, but when it comes to estimation, I have another structure that I'm going to show you that is advantageous for a number of reasons. Okay, so what do we want to do? We want to maximize the log partial likelihood function and get a partial score vector. And with my co-authors, we've shown that it has a certain score structure where we have a sum of vectors. The AT-1 matrix is a function of the covariates. It's block diagonal. And this BT vector is a vector of martingale differences involving the indicator for zero and you'll see some transform variables y star and yt star, as well as their conditional means on the next page. Okay, and so yeah, the idea is that we're going to, in principle, set this to zero and solve for the parameter theta to get our maximum partial likelihood estimator. And we'll need estimate of standard errors, and in this framework, we will derive the observed information matrix, so kind of like likelihood-based idea. And we've shown in our paper that there's a certain structure to that. It involves some matrices. Things were getting a little bit hectic, so I'm not going to show every single detail. So far, I have shown you AT-1 and KT-1, but very briefly. Things do get complicated in the sense that we have digamma and the derivative of digamma function in there. Uh, so we have an expression for the observed information matrix. And so again, in principle, what do? We use Newton-Raphson to iteratively solve this equation and get a maximum partial likelihood estimator for our parameters. Now, it's very typical in the zero-inflated literature to, instead of Newton-Raphson, to provide obtain estimates using an EM algorithm. That was not our initial submission to the journal, but the referee was very interested in that. So at the very least, we jotted down what that would look like. And so what does EM algorithm look like? Here, well, we assume that there's a latent parameter that's not observable, that given the past information is Bernoulli with success probability alpha t being the zero inflation parameter at time t. So basically a coin flip that tells you, given knowledge of ut, whether you observe a zero or a non-zero proportion. Okay, and that's why we've written down yt given ut and past covariate information, for example. We have some kind of a modified beta distribution. Ut is 0, we get our non-zero proportion, generate from that. If ut is 1, we get our degenerate distribution with point mass at 0. So to carry out the EM algorithm, we're going to need a predictor for ut, and an application of Bayes' rule gives us that expression, but really, what does it come down to? If we observe zeros, well, then we just get a 1 for this expected value. And if we don't observe zeros, non-zero proportions, we're going to get a 0. And so, there's separation. There's a orthogonal separation in the complete data partial log likelihood. So as you can see, we've got the two components. This complete data partial log likelihood is broken down into one based on the beta distribution and one based on the degenerate distribution. And then what is the approach in the EM algorithm? Well, we have to find the expected value at each step, given our predictor for ut, and based on our parameter estimates. So we do that, and then we maximize that component, and then we keep iterating between the E step and the M step. And because of this separation, this is very easy to do. What do we have in this first summand? We have basically the beta ARMA log likelihood, sorry, and the first component, first summand, and we have a logistic regression in the second summand. So we could use R to do that, separately at each step. And in particular, there is a package that's been very recently developed, ETSR, I think it's called, where you can do beta ARMA regression. Okay, so I had mentioned that it was advantageous to show that our partial score vector had a certain structure. Well, we do this, and it's very easy to show that our partial score process is a martingale. It's zero unbiased and zero integrable. In this partial likelihood framework, what's done is one derives the conditional information matrix and relates it to the observed information matrix, and under certain conditions, we get the asymptotics to be valid. And so in our paper, we've shown what that expression looks like. And here's where I ask that you look at our paper for the variance of this BT vector. It was kind of unwieldy, and I decided not to put it for the presentation down. And then we have 3 assumptions, very typical in the time series partial likelihood framework, for our linear predictors, and as well as for our conditional information matrix, which we use to get a theorem and two lemmas. The theorem having to do with the partial score vector, the lemma on the observed information matrix, and the other lemma on the unconditional information matrix. And putting all of this together, we convinced our referee that solving our partial score vector will give us an estimator that exists and is consistent and asymptotically normal. I have to say that our proof parallels that which you will find in Satish and co-authors in Statistica Neerlandica in 2022. And the referee was convinced by that. So effectively, if you want to see very detailed proofs, this is the paper to go to. And their result was on zero-inflated Markovian count regression. Okay, so I have to say, we did not, in fact, when it came to the numerical work, do Newton-Raphson or EM. What we did was we observed that our conditional score function is identical to the score function that you would get for zero-inflated beta regression for the independent or cross-sectional data in the paper by Ospina and Ferrari, Computational Statistics and Data Analysis, 2012. And that is helpful because there's already an R package, GAM-LSS, to compute the estimators for the zero-inflated beta regression for cross-sectional data. But you will interpret the standard errors that you get from that package conditionally. For model selection, we suggest, and this is again very typical in partial likelihood literature, you're going to penalize the partial likelihood in the same way that you do when you had a full likelihood. And there's in our simulation study, we take a look at these two criteria a little bit in detail. What do we do when it comes to residuals? Well, we use the randomized quantile residuals. And what are they? They're the probit transform of the CDF, the conditional distribution of the responses. And what do we expect to see? Well, if you have an adequate model, you expect to see residuals that are independent and approximately standard normal. And the reference for that would be Dunn and Smythe, 1996, Journal of Computational Graphical Statistics. So in particular, what do they look like for our mixture distribution? They look like this. They're randomized, so where's the randomization coming in? You will simulate from a uniform distribution on 0 alpha t hat if you have a 0. There's no randomization if you don't have a non-zero proportion. And this G here is the cumulative distribution function for that beta regression that I mentioned due to Ferrari and Crabari-Netto. Then in our simulation study, we looked at a few things, very typical things that we look at in simulation studies. We have a few different sample sizes to see what's happening with increasing sample sizes. These data sets were simulated 1,000 times, and we use the R-Bézier function in the GAM-LSS package in R. We have some settings for the mean parameters, the dispersion parameters, and the zero inflation parameters, call it rho. The structure of these linear predictors is such that we have a trend in the mean and dispersion, but we don't have such a trend in the zero inflation. And then we have some indicators. The indicators, if you look carefully, are for observing whether a certain lag is a non-zero proportion. And these will serve as our proxies for an autoregressive structure. So think of it as having an AR2 in each of the components for mu t, phi t, and alpha t. And then we collected some statistics, um, such as percent relative bias, coverage probability, empirical standard error, and asymptotic standard error. Okay, so I have a table, and I do not wish to overwhelm you with too many numbers here, but just the takeaway that we got from this is that at, at the very least for the mean parameters, the beta mean parameters, even for small samples, if you consider 200 to be small, at least the smallest in this group, we have percent relative bias under 1%. So that's doing well. It seemed to confirm our intuition that using the GAM LSS package would be all right, although some weird thing is happening here and here with the dispersion. Dispersion doesn't seem to be typically well as estimated. However, that does seem to improve somewhat with 500. Zero inflation parameters, they are being estimated well in terms of percent relative bias for samples of size 500. And then in terms of coverage probabilities, more or less, we're seeing some 95 numbers close to 95% for 500. Our motivating example has 800 observations. And then we're taking a look at the empirical standard errors versus the asymptotic ones, and seems to be doing reasonably well. They're matching the ASCs with the empirical ones, at least for large samples. And then in another simulation study, we wanted to see how well this AIC and BIC do when it comes to model misspecification and model selection. So in that simulation study, the true model is one where there's a linear trend in the mean, and they call it an AR1 serial dependence structure. There is an AR1 dependent structure in the dispersion, and the autocorrelation parameter is constant over time. And then we fit several models, mostly misspecified. The model that is correctly specified would then be for K1 equals K2 equals 1. And we wanted to see out of 1,000 simulations how well AIC and BIC would do when it comes to selecting the correct autocorrelation structure. And so this on this next table, so you'll see that in bold I have the row where the right thing has been done. K1 equals K2 equals 1, and AIC selects the correct AR structure, if you will, about 70% of the time for all the samples, whereas BIC does so, at least 95% of the times, and this motivated us to use BIC for model selection in the real data analysis problem. Okay, so back to our motivating example. we ended up using BIC and ended up settling on a model for the autocorrelation structure where there was lag 1 and settled on lag 1, lag 2 for zero inflation and tested, was there a change in the level? Was there a change in the variability in that last winter year? Was there a change in zero inflation in that last winter year? And as our sort of visual inspection suggested, yes, there is a change in the level, there is a change in the variability, but no change in zero inflation in the last winter year. So then we decided to look at some residuals. Well, if I use a cross-sectional model, both residuals for the cross-sectional and the time series models are normally distributed. Didn't seem like there was any point to doing zero-inflated, beg your pardon, a time series approach. However, if I inspect the sample autocorrelation function of the residuals, it looks like we've whitened the residuals and the approach was beneficial. Okay, so to summarize the first part, what we've done is to develop an observation time series regression model for proportion data that may on occasion take zero values using the partial likelihood framework. This approach is an extension of the zero-inflated. In fact, they had 0 or 1 inflated beta regression model for independent or cross-sectional data by Ospina and Ferrari in the 2012 paper in computational statistics and data analysis. Model fitting is easily accomplished via an existing R package, and you can see details of our work in the JSCS paper of ours that came out in 2024. So this is the summary of my part 1. I have a few more results on an extension. So if you bear with me now, I wanted to see what else we could do. Well, there are a lot of models for proportion data, actually. Another popular one is the simplex distribution. What else will you find? There's Kumaraswamy, there's unit Weibel. So this motivated me to think about, well, could we model at least the mean and the zero inflation parameter in a distribution-free way so that we don't have to try various parametric approaches. Here you're seeing, an estimated density of the simplex and the beta for the non-zero proportions. And so what I would like to do there is show you the distribution-free approach that I've just started to look at. So the simplex one, you may have or may not have seen it, but again, it's a mixture between the degenerate distribution at 0 and the simplex density function. I haven't put down the simplex density function down in the presentation, but if you want to see it, take a look at Barndorf, Nielsen, and Jorgensen in Journal of Multivariate Analysis. And very recently, a zero-inflated version has come about due to Liu et al. In 2020. In their approach, they did not model the influence of covariates on the dispersion parameter sigma squared, only on the mean and the zero inflation. Like so. So what I'm seeing is this. Oh, so we're in cross-sectional world. I'm just speaking, we'll start with the non-time series approach. The mean for the zero-inflated simplex, this is identical to the mean for a zero-inflated beta. So I thought, is there a way for us to estimate these parameters without variance specification? Because the variance, obviously, for the zero-inflated beta and zero-inflated simplex, they're different. But is there a way to identify the regression parameters uh, associated with alpha and mu without making any variance specification? In other words, some kind of robustness. And the approach that I'm going to explore is based on something known as functional response models. What are they? They say, look, if you can find a function of your responses given your covariates that identifies your parameter, then jot those down. You'll get an estimating equation and then use a generalized estimating equation inference framework to estimate model parameters. More on this you can find in Kowalski and two. It turns out they're U statistics, and you might say, "Oh, why are these subscripts like written this way?" It's a very general framework. You can find this framework in, for example, like a causal inference and mediation analysis. It's meant to break up the um, relationship as, oh, we have a response and then we have it as a function of the x's. We may have a situation where the response appears on either the right-hand side or the left-hand side, for example. And as well, we may have a covariate, not covariate, beg your pardon, a vector valued response. Anyway, it's very general. I don't go that general. I said, let's say, let Q be 1, and here's my version of the functional response model. Take F1 to be the indicator for a 0 and F2 to be Y, in which case the mean of F1 and F2, they do identify the zero inflation parameter and the mean parameter. So this would be the case if your data comes from a simplex, zero inflated simplex distribution or a zero inflated beta distribution. And what does the approach say? Well, we're doing something like a generalized estimating equation. So we form an estimating function S, the F vector minus its mean. Then we have a derivative of H. So we do need our H to be a smooth function as a result. And then we have a V matrix where the entries are diagonal entries are the variance of the Fs, and the off diagonals are the covariances of the Fs in our functional response model. Okay, and so because it's GE, you could have a working correlation matrix here. So finally, you get your parameter by solving the estimating function dV inverse SI summed over, we sum over these matrices for the parameter. And G guarantees that your estimator is consistent and asymptotically normal. And so how do we estimate the standard errors? That would come about by the sandwich estimator, and we would then have consistent estimators of the so-called the bread here, these bees, and the meat, what's in between. Okay, so that's how we would get standard errors. So does it work? How does it do? Here are my very preliminary results. I simulated from a zero-inflated beta regression model, just again, not time series. This is cross-sectional. I forgot to put down, but these axes were simulated from a standard normal distribution. Maybe I'm not doing something right here. I fixed the dispersion to be at a constant. I said, oh, suppose it's known. So my goal is to estimate the zero inflation and the beta. So that would be these minus 1 and 1 and sorry, minus 1.5 and minus 1 and 1. And it did this many times, I think 1,000 times, and we found our functional response model estimators, and on average, we are hitting the target. We're getting very small 2% relative biases here, under 2%. Are the empirical standard errors close to the asymptotic ones? In other words, are the ASCs matching the SEs? That's the direction we should think about. Yes, for zero inflation, not for empirical. So here I stopped here. I was expecting all the standard errors to match their empirical counterparts. I don't know why this is not the case here. Maybe my comparison is not correct. Maybe I shouldn't be fixing log phi and saying its parameters are known. And as a result, the mean parameters, the betas, are becoming highly inflated. I don't know. This is the question I have. Maybe somebody could mention some thoughts, but that is where I'm going. And to summarize, we're working on a distribution-free approach to zero-inflated proportion data. And if this works, then I will know how to adapt it for time series data, because I've done that for counts. And the idea is for us to model the mean and zero inflation without variance specification. What do we get? We get GE type because it's GE. GE estimators are consistent and asymptotically normal. Okay, so this concludes what I want to say in my presentation. Thank you.
Thank you so much, Dr. Ghahramani, for that wonderful talk and very insightful presentation. On behalf of everyone, I would like to express our sincere appreciation for your work and the time you spent today. So now's the time to answer the questions. We have a couple of questions in the message. Could you
Oh,
see them, or should I
yes.
read them for you?
Yes, I can see them. Yeah. So a very reasonable question. Why didn't you go for a, zero inflated binomial regression? I mean, yes, I think well, first of all, I was like, oh, I wonder if 37 is large enough for me to consider these as a continuous proportion. And it seemed to work with respect to the residual analysis. But then, I was thinking when I first looked at it, the beta distribution is very flexible. Okay, we could have skewed to the right, skewed to the left, what they call J shape, inverse J shape. That was my thought, that it's very flexible and would cover a lot more data types. Because when it comes to the discrete ones, I've seen extensions of zero-inflated binomial regression models because they're not adequate. I was thinking that the beta would be more flexible. So that, I have to say, was the primary motivator. And I have to tell the students, this is the kind of thing that can happen to you, when you get into an area that is new to you. I had not worked on the beta distribution before. You start with a certain way, and then you get more experience, and then you think, oh, maybe I could have done it better. I've had some suggestions made to me. I can say some other things about this. So one comment was, I'm seeing zeros in the middle of your winter year. Okay, and one researcher said, not convinced that's a real, that's a structural zero, as you're treating your before the winter year, at the beginning and the end. That's probably because the signal isn't strong enough. And that researcher suggested looking at the ordered beta distribution. So that extension is also possible. I'm seeing there's one more. Is there a question? Also log binomial regression. Okay, I should write this down and I should look into it. So yeah, in summary, I thought it would be more flexible, but I have to admit that it won't, these parametric distributions, they won't work all the time. I have fit this model to some other data, and we weren't able to fully whiten the residuals. So that's what got me thinking about a distribution-free approach. Although in that regression model, maybe there was a missing covariate or something like that.
Thank you so much again. Is there any questions by audience? We would appreciate it if you could write it on the chat parts as a message. And any comments, questions?
Yeah, so the question that said if the denominators are not the same, the binomial could be better. Okay, that well taken. Here, they're the same sites that are being observed. So yes, valid point there. I know it's typical to ask the uh, speaker questions, but I'm wondering if anyone has any thoughts on the distribution-free approach. I mean, um, if anyone has any experience with GE, or was it clear what I was doing there? Um, I think that I didn't explain maybe perhaps slide 47 very well. Or, you might ask, what did you take for your variances? Well, variance of F1, that's just the variance of the indicator function. Um, that's not a problem. The variance of F2, I have to propose a variance for the y's. So I took the zero-inflated beta distribution there, but I, I did that because I could easily simulate from this process. And what I'm trying to say is this is not the final goal. I want to derive something that is um, distribution free and robust to variance misspecification. I was just trying to see if I did something that's model based, would I get asymptotic standard errors that match the empirical ones? But that was not the case, and I have to sort out why that is.
All right. Thank you so much, Dr. Ghahramani, again for joining us today virtually. And as I've seen, there is no more questions. So again, I appreciate your work. Thank you for sharing that today.
Oh, thank you again, everybody.